Crude incompatibility that leads to fouling problems is often caused by changing the ratio of four crude oil components that are defined by polarity and solubility. These components are saturates or paraffins, aromatics, resins, and asphaltenes. The acronym SARA is often used to refer to the four components. There are three types of crude compatibility issues that refiners must be aware of. These are self-incompatible crudes, incompatible crude blends, and nearly incompatible crudes. In this seminar, we will discuss the unique characteristics of each of these compatibility issues, models to determine crude compatibility and to predict fouling, along with commercial options including software and analyzers will also be discussed. Irvi of Soluble Solutions has created the colloidal dispersion solution model, which shows how asphaltenes would normally behave in stable crudes. First, the asphaltenes, which are considered the solute, are dispersed by resins, the dispersant. Later, the complex is dissolved by small ring aromatics, the solvent, then later by saturates or paraffins, both considered to be non-solvents. The image on the right shows Wies' model. Self-incompatible crudes are those that are prone to asphaltene destabilization and fouling even when not blended with other crudes. Such crudes are more likely to cause fouling and processing problems than compatible crudes. More than 30 such crudes have been identified, including Mexican Isthmus grade, even though it has been recommended that refiners generally avoid buying self-incompatible crudes. The frequency of self-incompatibility observed for West Texas Intermediate is increasing due to accidental and intentional contamination. Intentional contamination occurs when tight oils are blended with West Texas Intermediate along with Canadian heavies to match the gravity and density specifications of West Texas Intermediate but result in the precipitation of asphaltenes. Since 2011, it has been found that 75% of West Texas Intermediate to be incompatible, compared to no incompatible samples found before 2011. To avoid self-incompatibility, it has been recommended that increased testing be done for compatibility as well as transport of crudes that are compatible with both light oils and heavy oils in between shipments of the latter two. Incompatible crudes are those that are stable individually but unstable when blended. When incompatible crudes are blended, a change in the ratio of the SARA molecules or an increase in the concentration of saturates such as paraffins may occur. Both of these events may lead to asphaltene destabilization. In general, mixing asphaltenic crudes with crudes that are more paraffinic, such as light tight oils, causes the asphaltenes to become destabilized. Crudes being combined in the wrong order is a reason for crude incompatibility. Other reasons for incompatible crude blends include incompatibility over some range of composition, and, for certain blends, high temperatures. Incompatible crude blends cause asphaltene and paraffin immiscibility, leading to asphaltene precipitation. This has numerous deleterious effects in the refinery, which include lowering of capacity in crude tanks, emulsion formation in the desalter, and fouling and coking in preheat exchangers, distillation unit furnace tubes, and catalyst beds. In order to avoid these problems when blending tight oils and heavy crudes, refiners should blend tight oils with heavy crudes with an API gravity of 13 to 16 degrees to yield a blend with an API gravity of 21 to 23 degrees. According to the oil compatibility model, which is one option for determining compatibility, nearly incompatible crudes have a solubility blending number to insolubility number ratio in the range of 1.0 to 1.3. Nearly incompatible crudes are likely to cause moderate fouling and contribute to rag layers or emulsion layers in the desalter, because nearly incompatible oils form smaller asphaltene particles than those formed by incompatible crudes. Nearly incompatible oils cause more stable water in oil emulsions. Thus, the smaller asphaltenes are able to more tightly surround water drops.